Welcome to this Architecture Today webinar, a roadmap to retrofit. Is EnerPHit the answer? With programme partners Schu. In a moment, your chair, Ruth Slavid, but first, let's get started with Schu UK's Commercial Director, Sean Butler.
Welcome to the latest in our series of 80 Schu webinars. In today's webinar, we will consider how we can develop and deliver pragmatic and affordable solutions to retrofitting our historic building stock. Now that the Passivhaus Trust has introduced EnerPHit standards as a potential blueprint for refurbishment projects, we explore whether the standards are a genuine option for building owners and operators wishing to update buildings to deliver high standards of living, as well as reducing buildings' energy demand and carbon emissions. Ever since the standards were first developed in 2010 by the Passivhaus Institute, it's been understood that a deep retrofit to EnerPHit standards can make a significant difference to a building's energy use. But would the widespread adoption of those standards by the UK construction industry be the most effective way to reach the government's carbon reduction target for refurbishment projects? You're about to hear from three speakers who will share their experiences and insights and weigh up the relative merits of EnerPHit with a less prescriptive green retrofit approach. Are there more pragmatic and cost-effective approaches for refurbishments, or is EnerPHit the best way to deliver long-term financial and environmental savings? We believe that Schu is one of the sustainability pioneers within the construction industry, but we know we don't have all the answers. So I'll be extremely interested to hear the presentations and discussions today. Thank you once again for joining us. I'll now pass you to Ruth, who is chairing today's event.
Thank you, Sean. I'm delighted to be here because I think we are talking about one of the most important subjects. If we are going to get anywhere near to zero net carbon, then we do need to tackle retrofit. And I know that where Passivhaus has had immense approbation and enthusiasm, although there are some people who believe it's not quite the right way to go, with EnerPHit, I think the question is even more complex because we are having to make the best decisions for our existing stock, and those can be complex. So we're going to hear some really interesting presentations, I'm sure, today. And I would just remind you before I introduce the speakers that you're likely to have questions, and do please send them in to us using the question button. We'll have some short discussions after each of the speakers has presented, and then at the end they will all come back together and we can talk. And obviously that discussion will be informed by your questions, so do please send them to us. We've got three speakers this morning. We will be hearing from Sanya Polescuk of Sanya Polescuk Architects, and we will be hearing from Rupert Daly of Collective Architecture. But first, I'm delighted to introduce our first speaker, who is Lee Marshall, Managing Director of Viridis Building Services. Lee, over to you.
Thanks, Ruth, for the introduction. Very much appreciated. As we said, Lee Marshall, Viridis Building Services. We do net zero. And I'm here to talk today about retrofit in all the different types of buildings in the UK, commercial, non-commercial, residential. One of the things I wanted to sort of mention as we got into this was lots of debate about climate change, Act Now, hashtag Act Now. Lots of groups out there really championing the environmental cause. That's a cause we really support. We really want to support now, and we really want to support further. One of the points I want to make on that is we've actually been acting for a long time. We're acting now. Myself as an engineer, I've been acting for the last 20 years. We've been doing net zero for a long time. Lots of our projects have been doing nearly zero energy or net zero from sort of the early teenies, 2012 onwards. And so I really feel that I should put a comment out there is, catch up, help us continue the fight that we've been fighting for the last 20 years or more. Not just me and my career, I know others in our industry that have been doing this for 30, 40 years, if not more. What I would encourage some of the groups out, environmental groups out there to do is target policy policy has been the big changer in the environmental movement in the UK in the last 20 years in terms of our commitment to net zero, those sorts of things. Target policy, target debate, but on a point, don't target the public. Don't prevent people from getting to the jobs. Don't prevent me from getting to my sites, my clients, where I'm helping them deliver net zero. So, you know, help us keep going, support us, because we are acting now, and we've been acting for the last 10, 15, 20 years, if you like. So I think I've said enough on that. I'll move on that point. We're going to talk a little bit about EnerPHit, and I want to talk about how that compares against our UK regulations, and perhaps identify that there's more than one way to skin the cat, as it were, and there's loads of opportunity for innovation within UK PLC regulations. Our regulations are set up that way to allow us engineers and architects to innovate and innovate within the goalposts that we're using to take us towards net zero and nearly zero energy all throughout the UK. And to do so, I thought I would be a bit techie for a moment. I thought I would talk a little bit about heat losses, and particularly the heat that's lost through a wall of a residential dwelling. And I've set out a little table, and I've kept it quite lay, and which hopefully helps explain it. And so what I've done is I've looked at EnerPHit, or Passivhaus, and I've looked at UK regs, okay, and I've said, if I just consider the wall of a building, and I consider the U value that wall might have under a particular condition of building regs, and then I compare that against, say, an EnerPHit or a Passivhaus building, and I do that on a winter's day, a really cold winter's day where it might be below freezing outside, but we want to keep the room nice and comfortable at 20, 21 degrees. And then I consider that again against a mild winter's day where you know, it might be 6, 7 degrees outside, so it's not so cold, but you still want to keep the room comfortable, a nice warm environment. Okay, so if I consider the winter's day to begin with, and I look at a U value of 0.25 and a wall area of 150 square meters, so that's the total surface area of the total wall area of the building. So take the windows out, all those sorts of things, that's the wall area that I'm left. And I say that I want to keep the building at 21 degrees inside and -4 outside. That gives me 25 degrees of a heating envelope I have to heat across. And when I look at that just for the wall, what heat is lost through that wall, so a building regulations wall, as it were, with a 100 mil cavity, with 100 mil of really good, high quality specified insulation in there, not a board, but a mineral wool insulation, then my calculation shows that I'm around about 940 watts. That's the loss I'm getting through that wall. And if I do a similar calculation with an EnerPHit wall or a Passivhaus wall with a lower U value of 0.15, for example, then my loss through that wall is less, because the U value is less, but not considerably less. And what that means is, you know, rather than say 940 watts, I'm around about 560 watts. So what does that mean in terms of each square meter of wall area that I've got? Well, my building regs house, for example, or my building regs wall, I lose 6.25 watts per square meter. So for every square meter of wall, I lose a few watts. And then with an EnerPHit or a Passivhaus property, I lose a few less watts. So rather than say 6, it's 3.5 or 4. Yep. And so the difference between the two walls is 3.5 watts per square meter. Now, that isn't a lot of energy per square meter of wall. And so if I think about how people live in houses, how they turn lights on, how they have ovens on, how they turn the kettle on, those sorts of things, well, that uses a hell of a whole lot more energy than 1 square meter of wall area, if you see what I'm saying. And then when I compare that to the energy that equates to across a year, for example, using some good engineering metrics and operational data, you know, that 3.5 watts per square meter equates to 350 kilowatt hours, okay, of energy. Now, if I consider a single photovoltaic panel at 250 watts, okay, and the output that gives me over a year, well, then that's 200 watts. 200 kilowatt hours, I should say, which is quite close to the savings made by putting plenty of insulation in the wall. So if I use 2 panels in this instance, then I've offset the savings that extra insulation generates. Okay, and then when I look on a mild day, if I look at my mild day here, you can see that a similar comparison. But on a mild day, my saving with a really well insulated building is a lot less. It's only 1 watt per square meter of wall area, which transpires into about 120 kilowatt hours per annum. And then if I look at 1 PV panel, then you can see that 1 PV panel on milder winter days more than offsets the energy requirement for that element, that bit of building fabric, as it were. So it's a very, very strong point. And this is working within UK PLC regulations to achieve this. And so when I think about the cost of the investment of the additional insulation in the wall, the extra thickness of cavity, the foundations, the buildability of that, the non-standard buildability of that, well, I can achieve a very low energy building. I can achieve the same outcome as an EnerPHit or a Passivhaus, working within the same goalposts, but perhaps at a lower cost, and deliver the same outcome. And that's what I wanted to sort of demonstrate in this little example, okay, as a sort of a method for debate, if you see what I'm saying. So it's not that we're anti-Passivhaus or anti-EnerPHit or any of those sorts of things, but we're pro the outcome that those franchise license systems promote. We're pro the outcome of that. We're pro the outcome of that through different routes and means to achieve that. So as another example, it might be, let's say it costs, £250,000 to build an EnerPHit, a Passivhaus, or refurbish it to an EnerPHit standard. But I can achieve the same outcome £50,000 cheaper. That means I can do more houses with the budget that I'm saving than not. So for me, from a sustainable perspective, balancing people, planet, and prosperity, the environment, the techno-economic issues around the solution means if I can do more, with less, then for me that's a real positive, sustainable outcome. So I also want to talk about MVHR a little bit, because as an engineer, as an expert in heat transfer and air movement in and out of buildings and the wetness and dryness of air, I just thought it'd be important to touch on some of the misnomers on this technology and some of the advice that perhaps the industry isn't alluding to or talking about. So what's critical to know about MVHR is that if we're thinking about domestic MVHR in the UK just now, the air streams do not touch. They pass one another through a heat exchange or a heat cell, as some people might call it. Okay, what this does is it limits heat transfer to conduction only. So I've got an amount of wet energy in there that I can't get across that plate because it will not conduct across it. So this conduction transfer is limited to 35% typically of the available energy in the air. Okay, and that wet bit I'm talking about, I can't get across. That's the latent heat transfer. The wet bit of the air, the moisture bit of the air, I can't get across. And typically that's about 65% of the available energy. So when it comes to MVHR efficiency, MVHR is 90% efficient of 35% of the available energy. Now, that's technically correct, and that's what it's sold on, and that's what it promotes it on, okay? And there's nothing wrong with talking about that because it's technically correct. But a lay person or Joe public may not fully appreciate the physics and the fundamentals behind heat transfer within that technology, and may be misled into thinking that it's going to heat their home and all those sorts of things when it doesn't. It helps to recover heat, but you have to add additional energy in to keep comfort temperatures within the dwelling. So MVHR, when we think about fan consumption, leakage through the ducts and those sorts of things, is at very best 30% efficient. And I would encourage you to ask your MVHR suppliers to explain the difference between the net efficiency, which is 90% as it were, or the gross efficiency, which would be 30, 35% or less. Yeah. And if you get any response and you want to have a conversation with me about it, please do. I'd be more than happy to hear from you. So I just thought I'd touch on that and be careful of white elephant gift exchange. I just thought that's a bit of a play on something there, and probably been quite naughty, but we've got to throw some fun into these things at times, haven't we? So we'll move on from that then and talk a little bit about Part L, okay, in particular criteria 3, right? This has been in our armory of legislation, regulation in the UK for numbers of years now, at least 10 years. And criteria 3 of Part L of building regulations is quite clearly about the avoidance of air conditioning and the prevention of overheating, and using passive sustainable means to do this. We have had this in our legislation for years, yeah? And we as architects, designers, those sort of things, perhaps need to re-review what that legislation says and encourage now use of criteria 3 within our building design. Using it, we can design out lots and lots of M&E systems that are unnecessary in those types of buildings and drive energy out of the building, following a fabric first approach such as EnerPHit, Passivhaus, or really being innovative within our own regulations. Criteria 2 is about our limiting standards. So that's our U values, our pressure test, those sort of things. Now, the limiting standards of criteria 2 and the criteria 3, the avoidance of overheating, they are statutory guidance, meaning these are the rules, but it's up to you how you implement the rules. So there's loads of availability for innovation in that. I keep coming back to that. Those are the sort of nudges, if you like, in the regs to say, well, here's how you could do it. Here's what might happen if you use this, those sort of things. But it's just up to us as designers and innovators and creatives to implement those regs in a way that works to meet our project aspirations, as it were. And that brings me on to criteria 1, which is a very important criteria. And not a lot of people get this. I'll pop down. Criteria 1 of the building regs is the lawful requirement. That is the thing within Part L that we must achieve. How we achieve that? Through our limiting standards, criteria 3, the flexibility that gives us is entirely up to us as designers, creatives, and innovators within our industry. Okay? And what criteria 1 says is that, in simple terms, is your CO2 emissions of the building that you're designing must be lower than the government CO2 emissions for a building that is exactly the same as yours. So your building you're designing has to be more efficient than the same building that the government has designed, as it were, to fit in with the regulations. That is our only lawful requirement. We've got to get our CO2 emissions down based on a notional standard generated by some government software. That is the legal definition, and that is what we're lawfully obliged to do as designers, innovators, creatives. How we do that? We've got criteria 2. We've got our U values, we've got our limiting standards. We can be flexible with those. We can either go really low, we can go to EnerPHit, Passivhaus standard or beyond. Yeah, we can be a little bit, more creative. We can accept a lower U value because we maybe have some more renewables on site, which helps us achieve our net zero standard or our A or B or C and our EPCs, as it were. Okay, how we do that again is entirely down to us. So it's a really important point, that, and I think hasn't been promoted enough in our industry to show how innovative we can be within the regulations that we've got here within the UK without trying to adopt other international standards or European standards. And incidentally, I've done lots of research on U values and energy efficiency around Europe, and we all work from all the member states. Of course, we're not one now. All the member states, including us when we work to the same European Performance of Building Directive to develop energy efficient measures, including our SAPs or SBEMs or U values or limiting standards. And if you look at what France does, what Germany does, we're all on the same path, we're on the same trajectory. So we've got the wherewithal, the skills within the UK to do this ourselves, and we should be doing if we super understand what our regulations and legislation says. Anyway, bit of passion there, a bit of soapbox, but it's all good fun anyway. So, what have we got to do then? Well, there's some good challenges out there, such as the REBA 2030 challenge, a great UK challenge to help us drive operational energy targets down in buildings. So there's different targets for commercial buildings and residential buildings. It looks at embodied energy, looks at water use, and it looks at health and well-being. Lots of great metrics in there. Okay. The REBA 20 challenge has been around for a few years now. and a great challenge to get involved with. So some examples of net and near zero energy in practice, using the rules and innovation that we've got within the legislation, some from our own practice. So NSDC, New Yorkshire District Council, their new HQ building, we did that back in 2013. Operational energy, 41 kilowatt hours per square metre per annum, smashing the REBA 2030 challenge. This is a direct electric, all electric building, no renewables, fabric first, BREEAM excellent, smashing the REBA 2030 challenge with a very, very, very low energy demand. It just shows you what you can do if you work to fabric first principles and understand how to manipulate building physics to eliminate mechanical electrical systems from buildings. Incidentally, the M&E install on this building, or public sector building, was less than 12% of budget. Absolutely smashed it. Normally you'd expect somewhere between 25 and 30% of budget. Okay. Was on. That's just a little bit more about the project. But one thing I wanted to show was the frontage of the building. Now, to the side there, you can see a great big flank wall with the signage of the council on there. Now, that wall isn't just a wall. That wall isn't any old wall. That wall is a passive cooling device. That wall keeps the offices behind that wall cool all summer. There is no air conditioning in this building. It's naturally ventilated. And using passive devices like passive walls, stone walls, cooling walls helps to keep buildings cool. And we can be more inventive with our architecture and how we create buildings to build in those passive devices, techniques that help the form and the function of the building throughout the lifetime of it. That's free cooling now for the lifetime of that building. Absolutely fantastic result for the building. Okay, and a few other projects there where either refurb of leisure centres, banged out old 70 office buildings, bringing them up to scratch, educational establishments, those sort of things, where using those rules that we talked about earlier, understanding what our lawful requirement was and is going forward, how we can achieve nearly zero energy to transition to net zero energy and to really meet or smash those sort of targets that REBA is setting for us. So that's Lee Marshall, that's me, having a bit of a soapbox moment, I'm sure, on a few things. Really passionate about our industry and really pleased to be involved in this debate and looking forward to the conversations thereafter. Thank you very much.
Thank you very much, Lee. And I think that's a lot of food for thought. We've got a few minutes for questions now between the two of us. And I'd like to ask you to answer a couple of questions that we've got here about the trade-off between PV and higher levels of insulation. Sort of one question is to do with the fact that, does it matter when you're saying PV generates this much, that actually you're generating a lot of it at a time when you don't need the extra warmth that the insulation would have given you? And the second question that's come in also on PV versus insulation is it not better to insulate your building rather than to put PV on? Because with luck, the insulation will last the life of the building, whereas we don't know how long PV panels last, but I don't think they're going to make it through the life of the building without replacement.
Yeah, I think those are both very good questions and very good points. When it comes to the sort of the generation of PV across the year, that is just an example of an alternative approach to meeting the energy standards within a building. Energy isn't a daily thing or a weekly thing. Energy in the buildings is an annual thing and a lifetime within the building, and it's important to look at it across those across the years, as it were. One of the big energy users in modern buildings now, particularly residences, is hot water generation. So, for example, if we're producing plenty of PV energy through the sort of the warmer months of the year, the sunnier days, as it were, then that goes to offset hot water generation, which is arguably a larger energy use in buildings than perhaps what we're losing through the fabric, as it were. If we come to sort of the lifetime of PV, for me, the building is a technology, and if we look at how buildings are built just now, I suspect one can argue that our buildings built to last at present, and if we consider that a piece of technology which evolves, which grows, which contracts, we consider that as a piece of technology, then all the technologies, including the building, will evolve and change over the life of the building. And so I think that it's probably easier from a mechanical electrical perspective, renewables perspective, to retrofit technology onto buildings to drive up energy efficiency, rather than start to, for want of a better description, bash buildings about. So I think it's an option. And it's how we consider those options within the sort of the toolbox that we've got. We've got the tools here in the UK to deliver net zero. We've got the technologies, we've got the legislation. So it's really how we apply it, I suppose, I would say.
Thank you. I'm going to ask you one more thing before we come to the next speaker. And this is somebody who's come in and is saying, basically, why are there so many different retrofit targets? Now, I'm reading from this, so if the figures are wrong, I apologise, but they're saying that the LETI best practice, pragmatic, affordable and realistic level of retrofit and AECB talk about 50 kilowatt hours per metre squared. That Energy Sprong says 40 kilowatt hours per metre squared, whereas EnerPHit is much more demanding at 20 to 25 kilowatt hours per metre squared. Sorry, that's all per metre squared per year. I apologise. But obviously that we've got 50, 40 and 25. Those are quite different figures. And I just wonder what you feel about those.
As an environmentalist, I think they should be zero. I think we should be getting it as lower than what EnerPHit and the other guys are challenging there. But I think the important point is that we're transitioning to net zero, and it's going to be a step-by-step process. The last 20 years have been a great transition to this point, and I think the next 25, 30 years will be another great transition period for us in the energy revolution that we're going through to take ourselves net zero.
We will have a chance to talk again because we are all coming back together at the end of the presentation. So I look forward to seeing Lee again. And if you have more questions for him or questions for our subsequent speakers, do please send them in as they occur to you. Otherwise, you'll forget them. Anyway, I'm now delighted to move on to Sanya Polescuk of Sanya Polescuk Architects. Sanya.
We have been remodeling and retrofitting UK buildings for close to 2 decades. Our first notable project focusing especially on retrofit won the NLA Don't Move, Improve commendation back in 2012 and AJ Retrofit Award in 2013. It is a mixed-use Victorian muse house with a studio, our studio at ground, originally occupied by horse stables, and a maisonette above where horsemen and family used to live. The maisonette works now as a house in multiple occupancy. It's a diagrammatic section, environmental strategy diagram here, illustrates our attitude to retrofitting as was at the time. I believe our approach was pretty holistic and rather granular already, especially where it came to thermal upgrade of the fabric. I fear that not a great deal changed in the construction world of retrofit since then. What has changed and keeps changing is the various benchmarks designed to stimulate reduction of industry's carbon footprint. You can see at the top of the image referencing to then relevant code for sustainable homes. Our motto back then, I believe before the term fabric first became widely used, was wrap up warm and ventilate. I say that in order to illustrate the importance we always placed on understanding the nature of the building fabric we are about to work with. For instance, a solid wall construction built from breathable materials such as soft brick and lime pointing requires very different approach to retrofitting than a cavity wall built with hard bricks and cement pointing. With solid wall construction, the most important concern is to maintain its breathability. This requires either using breathable insulation or providing a well-ventilated cavity between the old fabric and the new insulation. Fast forward to the more recent days, and this diagram shows our last year's project involving cavity wall construction. But I'm actually showing it to you in a diagram form to illustrate how first, even before looking at the fabric and the operational energy of the building, we look at the site's orientation and shading with the view to its potential for energy generation. In comparison with our work from 10 years ago, this project shows more elaborate methods of solar harvesting, for instance. The site's southwesternly orientation at the rear meant that it could house both solar thermal and photovoltaic panels without affecting planning constraints. So we practically tiled the rear slope of the main roof with the inline solar panels. We added some more onto the roof of the new garden studio on the far right, and then further few over the roof on the rear extension, where you can see pointed at them as a figure of 2. That way, we definitely reduced the building's operational carbon. But the most valuable contributor to the reduction of carbon has been our inclusion of an air source heat pump. We used it in place of a gas-powered boiler, making the project entirely fossil fuel free. That said, trying to actually install the air source heat pump in a conservation area is not for the faint-hearted. I personally just wonder how is the Prime Minister's air source heat pump stimulus package going to work. In case you haven't heard yet, every household that scraps its gas boiler by 2035 and replaces it with an air source heat pump will receive up to £5,000 cash incentive. Well, I'm afraid, based on our experience, it's hard to see that working in any conservation area or any area of outstanding natural beauty, or indeed anywhere in the curtilage of a listed building. It won't work unless, of course, there is a fundamental change in outlook of the planning system. The planner's advice we had about installing air source heat pump has been rather predictably off-putting. One of those, these objects are incongruous with the character of the area, whichever area that may be. They should be located out of public sight. And why don't you just put it in the back garden? I think that is a really bad idea. Placing a pump in a garden reduces the quality of peace and refuge that gardens provide us with in our urban areas. We only managed to overcome the intense resistance to placing the pump in front of the property by designing this shroud, which references the original color gas niche on the front facade of the building and pointing out at the very utilitarian nature of both before the objection was finally dropped. So perversely, The new rear extension and the new studio building would jointly increase the area of the build by close to 25%, with all of their new solar panels, caused far less trouble in planning terms than our placement of one small air source heat pump in the front. Not only was the look of the pump a problem, but also the level of potential noise that it might create. And despite the location of the property next to one of the busiest crossroads in the neighborhood, and the manufacturer's low decibel ratings of the machine, the planners also asked that an acoustic report be commissioned and submitted. This, of course, added to both the cost and the time associated with its installation. But we worked with a sustainability consultant right from the front, from the beginning. The moment we realized there was a potential for the energy self-sufficiency, we knew we needed assistance from a consultant other than ourselves. But it was necessary to work with a sustainability consultant, not only in order to determine the energy strategy, but also in order to run checks on the fabric improvement strategy. We knew we were in the realm of deep retrofit with high levels of airtightness, and that cavity wall construction presents both good opportunities and plenty potential pitfalls. The risk of causing condensation, interstitial condensation in walls, could only be determined through hygrothermal performance modeling, a mouthful, otherwise known as WUFI. This is because, unlike with solid wall construction, where by and large we use a single manufacturer product and rely on either its breathability or our careful detailing of the fabric's ventilation alongside manufacturers' U-value and dew point calculation, with deep retrofit of cavity walls, we use multiple products. Typically, this is blown insulation in internal cavity, and in addition to internal phenolic insulation. Well, no manufacturer will run calculations using products they don't produce. So WUFI really is the only way of safeguarding a potential risk of interstitial condensation in the work of this kind. In our case, for instance, the modeling did indicate a potential for moisture buildup in the north-facing external brick skin during the cold winter months, and this was a risk we needed to overcome, and we were advised to use additional brick sealant, which we did. The process of improving thermal performance of the building envelopes includes the elimination of uncontrolled drafts. Into such well-sealed envelopes, it is then necessary to introduce a healthy dose of well-controlled background ventilation together with a good amount of purge ventilation, openable windows. We achieved this by specifying all windows and skylights as both triple glazed and fully openable, so they work in conjunction with the whole house mechanical ventilation with heat recovery, another mouthful, MVHR, and you can just about see its presence in the white circular item on the brick wall above the kitchen units. This combination further reduces the operational carbon as MVHR reclaims the heat from the stale air before expelling it into atmosphere and uses it to warm up the incoming fresh air. Finally, our quest to minimize carbon places really high value on the adaptive reuse and reclamation. So we retained and restored all original doors and repurposed the original stairs. We also had the original hardwood floor lifted, cleaned, and reinstalled over the newly insulated subfloor with underfloor heating included. Externally, the mid-century concrete pavers were pressure cleaned and relayed into the dry mix sand cement. In combination with new Ketley brick pavers, they provide permeable hard landscaping, which is kind to our overwhelmed urban rainwater distribution system. So the holistic retrofit with a common sense approach, the kind we have been slowly developing over the years, achieves a great deal for the clients and for the environment. Great majority of our clients' aims and aspirations are for more efficient buildings and lower bills. They tend to not care for certifications.
And I think that last point about not people wanting better performing homes rather than certification is really interesting. I wanted to ask you a little bit about air source heat pumps. You talked about the planning difficulties, but surely there are other issues as well, aren't there, with installing air source heat pumps without expertise, at least, which is to do with the changes that you're going to have to make internally in a building, especially if you have a building where you're not doing as radical a refit as you have been doing on this one.
I do believe that an air source heat pump on its own is not going to provide the substantial reduction of carbon that the government and all of us should be looking at. So I think it is just one part of the fabric first approach, together with reduction of drafts in the property, because air source heat pump can cope with temperature differentials, but it'll guzzle electricity if it has to cope with extreme outdoor temperatures. And just to tie in with Lee's point, you know, we in UK are rather blessed with not having too much extreme temperatures, and indeed the Passivhaus standards are based on continental extremes. However, if we can reduce the contrast between indoor and outdoor temperatures by making the fabric better insulated, that will place much less strain on and demands on the air source heat pumps. So I would say I wouldn't plug in an air source heat pump on its own without first doing at least something to the fabric itself. You should resist too many radiators and really use the temperature that heat pump produces and use it in underfloor heating. So yes, it's not a plug and play item.
And I mean, the other thing is, you know, we looked at that lovely project of yours and we looked at the amount of love and attention that went into it. And, you know, it's marvelous. I mean, you're talking about, you know, the importance of working with a sustainability consultant. And I'm just thinking, you know, if we really want to retrofit so many homes, have we got enough sustainability consultants to do it? Have we got enough architects to do it? Never mind, have we got enough builders to do it? I just think it's really sort of bringing up the scale of the challenge that is ahead of us. How do you feel about that?
Absolutely agree. We have tried diversifying our sustainability consultant pool, and it's been practically impossible because most sustainability consultants are geared towards number crunching and certificate provisions for large projects and commercial projects, and very few are interested and willing or have a capacity to deal with small-scale domestic retrofit. So yes, this is probably a call out to the consultancy industry. Please diversify downwards.
That's fantastic. Thank you very much. And of course, you will be coming back and joining us again at the end. But before you do, we have got our last speaker. Do again, everybody, please, if questions occur to you, send them in, because we will be discussing them at the end. And our last speaker I'm delighted to introduce is Rupert Daly, who is an architect with Collective Architecture. Rupert, over to you.
Just going to talk about, would say, multi-story flats, and we've titled it Bridging Thermal Inequality. But essentially, the bit I wanted to talk about is the process that we've taken in the journey with regards to the EnerPHit standard. So initially, just starting out, what is EnerPHit? Well, for us, it's simply a methodology that informs the design team how best to optimize the design to meet a very low energy demand and a high level of comfort. So it allows us to assess the design at a bit of a granular level, and allows us to actually have conversations with the client, with the design team, that we wouldn't have had before, because no one's really looking at it at that level of detail. The simple principles of Passivhaus or of EnerPHit is really shown here in this thermographic image. So on the left-hand side, you have a vacuum insulated thermos, and you pour in the heat, the energy, and with the lid closed, it will retain that energy for a long period of time. On the right-hand side, you have a cafetiere where the energy is continuously being inputted or fed into the machine to keep the liquid hot. So Passivhaus on the left, business as usual on the right, where essentially we don't have that high level of energy efficiency and we need to keep plugging away with more inputs. So we get it right, we'd get very low energy demand for space heating. Transfer that into a building level, and it's a similar graphic that we get in the thermal imaging. So the building in the front is a 1980s conversion with minimal insulation, and you can see the leakage that's coming through the building fabric in terms of heat and heat loss. And then in the background is the woodside multis, and we've got a very even blend of temperature across the surface, so it shows we've got continuity of insulation. And there's a couple of little red bits there where occupants have opened windows. So why did we look at the EnerPHit? Well, there's obviously the climate emergency, and what's governed from the Housing Association side is minimum compliance standards that they need to meet, which in this case is EnerPHit, which is Energy Efficiency Standard for Social Housing in Scotland. But on a project level, fundamentally, the main reason that we're driving this is to mitigate fuel poverty. These 3 multi-stories were built in the 1960s, and they predate the introduction of insulation to the regulations. They were cold, drafty, and very expensive for the tenants to keep warm or try to keep warm. So by tackling the EnerPHit standard, what we hoped to achieve was extremely low heating costs despite rising energy prices, which we know is in media currently, and we're all affected by the actual change in utilities. A very high level of comfort, high levels of structural longevity. The standard means that we should mitigate the potential for mold within the building fabric. We have a continuous ventilation system with heat recovery, so we're not achieving energy efficiency by compromising the indoor air quality for the tenants. We're making sure that they have the best healthy air conditioned space that they can have. So the compliance route on the right hand side is EnerPHit, and that's a minimum compliance. And the problem with that is because it's a minimum compliance, it's the standardization of assessment across the industry. And it means there's lots of gaps within the actual assessment criteria, and there's not really a design tool, it's just an assessment tool. So you're not really having conversations about energy efficiency, you're having conversations about ticking boxes to meet the actual minimum requirements. The other thing with this minimum requirements basis is, for the beginning of this project, the standard that they were needing to achieve was set for 2020. So we've already surpassed that, but the guidance would have been such that you're actually just trying to meet that 2020 standard. And it means that you're potentially locking in poor building performance upgrades which means that for future standards that are set, you haven't actually established a route map for getting to a much higher level, and it might mean that there's abortive works. So from the outset, we had discussions with the client and saying, well, actually, what's important here? What's important is mitigating the fuel poverty and future-proofing the building as best we can within the budget that we've got. So we brought in the EnerPHit as an assessment methodology so that we could actually have those conversations and look at where we could prioritize the value in the works. So essentially, fabric first, a holistic approach. We're making sure we're joining all of the dots, making sure that all of the insulation is continuous and we're getting the air tightness and the ventilation for the occupants. And that is prioritized over the addition of other things such as renewable energy generation. The step EnerPHit has options, so you can do everything at one time, or you can do it in a step-by-step approach, which we think for retrofit is actually going to be the mainstay, where budget-wise, housing associations, councils won't have the budget to do all properties, all the work, all at the same time. So it will be a phased integration over a period of time. So by the stepwise methodology, you still do the full assessment as if you're going to retrofit the whole building. That gives you your route map. And then what you can do is actually set out a plan on how you're going to get there. So you can implement it in stages. You could do the windows and doors, for instance, then maybe the roof and floor, and then the external wall insulation. For this project, we felt that it was best to do as much as we could at the same time. So it actually reduces the potential cost of multiple prelims and coming back, especially when we're talking about mass climbers and 22 stories of maintenance to actually get up there and do the work. The the EnerPHit standard is very similar to the Passivhaus new build standard. There's just slightly relaxed targets. So this air tightness requirement is less than 1 air change per hour, which that in itself is no mean feat. The new build standard is 0.6, but achieving 1 is still a really high benchmark to try and achieve. Space heating standard is to be less than 25 kilowatt hours per square meter per year, whereas the new build is 15. And then the MVHR is the same, and all of the other comfort criteria are the same. So why EnerPHit? Well, essentially, it's actually the most cost effective for the most energy effective building. In order to be able to access potential grants for certain renewables, we had to improve the building fabric to a minimum compliance level. In doing so, we just felt that if you're doing that work, let's just do it properly, and rather than just tick the boxes for compliance, and make sure that you're getting the maximum benefit out of the minimum material input that you can. So by using the EnerPHit, it allowed us to make sure that we're carefully looking at all of the details, all of the junctions, making sure that everything actually connects. The main time period in EnerPHit is really in that high level of design analysis. So you have those conversations which you never had before, but that's what's important. And that's the only way we're really going to achieve optimum energy efficiency. And then what also, it really just makes sense that in terms of the EnerPHit, you have to get the building fabric right before you consider putting renewables. You can't use renewables to offset poor building performance. That's just nonsense, but unfortunately that is the industry standard. You can build a poorer quality building, throw a couple of PVs on and meet the compliance requirements, not in EnerPHit. So using the EnerPHit principles and how they've applied to this type of building. So initially we looked at the form factor, which is essentially the amount of thermal envelope that you have as a relationship to the treated floor area internal. And you don't really get a more efficient building form. Each flat here has on average about 33 square meters of external surface area, or where the heat loss can occur. And that's really, really small if you compare that to, say, a detached house. It's a much smaller element. And that in itself means that in order to achieve the energy efficiency, you need less material. The better that you can make the form factor, the better. The less material or insulation you need to achieve that target. So what we found was the form factor drove the economics of the project. So we actually only needed to put on 120 millimeters of rock wool external wall insulation to the main elevations. And then on the narrower gables, we put 160 millimeters of rock wool. And that was actually just to make sure that those flats, which have a little bit more surface area for heat loss, are compensated for. The thermal bridges, we designed out as much as we could. If you don't have a thermal bridge, then you don't have a cost to deal with, quite simply. There are some that we had to maintain, so we had to calculate them and can keep them in the energy balance. The orientation is already set. We're not going to be able to move the buildings, but we do need to consider how, when you've got an energy efficient building, how the impact of solar gains could impact on the building. So fortunately, the actual building form had a reasonable amount of shading. So we're blocking out summer sun, which we don't want, but still allowing winter sun to come in. The ventilation system, so Passivhaus EnerPHit requires mechanical ventilation with heat recovery in the UK climate. And we opted for an individual solution per dwelling, primarily because trying to get in a communal system was going to be pretty challenging with the existing structure and floor to floor heights. The air tightness was surprisingly good and up to essentially current building regulations, but we still needed to make it quite a considerable amount better to meet the EnerPHit standard. So just looking at the form factor quickly, if you look at the left-hand section, that's the pre-existing section with recessed internal balconies and projecting amenity balconies. And by actually, on the right-hand side, what we've done is we've taken the quickest route or the shortest route for the insulation continuity as the vertical plane right down the elevation, where we've had the projecting slab for the projecting amenity balconies. We've wrapped that in insulation. We did talk about removing those at one point, but then we would have had a loss of amenity value. So there's a pragmatic discussion there, and occupant surveys and consultations to ensure that we're not just meeting the energy requirements to the detriment of other functional requirements of the building. But in actually glazing in the recessed balconies, we managed to reduce down the heat loss area by about 20%. So again, that translates into less material requirement, and it also translates into less cost because we don't have to deal with challenging thermal bridges because we've just designed them out. The amenity balconies during the contract, which was a contracted design element, required the addition of steel outriggers for the ceilings, and they needed to connect back to the main structure of the building. So in order to mitigate the energy losses of these punctual thermal bridges, the steel is fixed through a 50mm insulated structural packer, and that way we can minimize the amount of heat loss through this point. The air tightness target we'd mentioned, in this diagram here, the large square dotted dashed line is representative of the pre-existing condition. So that was about 5 air changes per hour, and that's a square approximately 21 centimeters by 21 centimeters at the pressure, at the 50 pascals air pressure test rate. To get to the EnerPHit standard, we need to get that down to essentially the size of a post-it note for a 75 square meter flat. And the smaller grey square is the extra over that you'd need to go to if you're going to a new build. The air tightness element in Passivhaus is not only for the energy efficiency, but it's a function of quality assurance on site, and it helps to ensure that there is care and detail being considered. For simplicity and a pragmatic approach to the air tightness, we have a pre-existing precast concrete cladding panels, which in themselves are airtight, but it's just all of the junctions that we needed to focus on. So we've sealed up the little drainage holes, which are no longer required because we're applying external wall insulation, and we've applied a flexible mastic to all of the junctions and the joints between them. The next element that needs to be resolved at scale is the repeatable junctions. So windows. Initially, we weren't going to replace the windows, or the client didn't want to replace the windows because they had about 8 years left before the maintenance replacement cycle. But this photo alone was enough to convince the client that it was necessary at the same time. So these were the existing double glazed units, and you can see even with double glazing that the junctions are a key issue with heat loss, when no one actually thinks about how these expensive components actually get joined or to the adjacent or interface to the adjacent building materials. So you're bypassing all of that benefit of energy efficiency in a high cost component by poor installation. So when we came to looking at the triple glazed windows that were coming in, we spent quite a lot of time on the first dwelling, just testing the actual product and testing the installation to make sure that it was airtight. And then had the insulation, external wall insulation, had a good continuous overlap with the frame to mitigate the thermal bridging allowance around the window itself. We realized also by doing these testing that manufacturing change by the local manufacturer, where they changed the hinges, and discussion with the contractor was actually compromising the air seals. So for £8 a window, the hinges were changed back to what they were originally proposed as a concealed hinge. So the working detail here, just zooming in on the previous sections: continuous insulation, overlap with the window frames to make sure that we're mitigating the losses of the interfaces, thermal structural packer for the steel outriggers for the canopy for the balcony. We do have a thermal bridge, even though we've wrapped the floor projecting concrete slab with insulation. It still has a heat loss component to it because it acts as a thermal fin, but we've reduced it down as much as we can and made sure that where the balcony winter garden connects to that, it's isolated with isolation material like a membrane and a plastic. The top left heat balance indicates where all of the heat losses for the building occur, and you can see there's a fairly even spread there, even with good air tightness and heat recovery ventilation. Infiltration ventilation takes up quite a large portion of those heat losses, but it's absolutely necessary to have the good quality air ventilation for the residents. The red box indicates the residual heating demand, so that's that 24 kilowatt hours per square meter per year. But when you get down to really good energy efficiency levels, you can see that the internal heat gains and the solar gains through the windows actually form a valid component to offset the losses. Whereas in a more leaky building, they have a much smaller function. The building's also all electric. There was discussion at the start of maybe going to a communal gas system. Fortunately, that was too expensive, and it's remained as electric. And that's actually going to be good for the long term because the carbon emissions associated with the electricity grid are now less than the gas carbon emissions, and they're set to come down significantly more over the next 10 years. So it's going to be much better performance in terms of carbon emissions than it would be if it had changed to gas. Progress shots, external wall insulation with the base render coat. So what we're aiming for here is full continuity of the insulation, and we've taken care around the windows to make sure that you're getting that interface of insulation to the windows before all of the external cladding elements for the winter garden are put on, so they're not compromised by that structure. Progress to completion shots, and then just lessons learned. So there's a few here, I'll let you read through them, but there's 4 that I wanted to really pick out from this. One is the tool that we use is essentially the Passivhaus planning package, which is a series of Excel spreadsheets, so we can input all of the data and takeoffs from drawings and specifications to build up that picture of what the energy balance is likely to be. So that is for design teams, I think that is the fundamental tool. You know, if we can use that, then we can have the conversations with the design team and make valid sort of decisions around energy and benefits for the residents. The form factor, so if we're talking about multi-residential retrofit, the form factor is an asset, and it's going to make a huge difference to the energy performance and the cost. For this project, the overall project value was 13.5 million, but just over half of that was associated to energy efficiency. And that's worked out about £290 a square metre. So I think that's probably the most cost effective and energy efficient project at scale that I'm aware of in the UK at the moment. The refurbishment is obviously going to be a bit of a challenge. In this case, the main challenge was that all of the works were carried out without decanting the occupants. So there was works internal for the MVHR and the new heating systems, as well as obviously replacing the windows. But I think it's important that we don't repeat historic mistakes of moving people out to do the works. So it's something that we need to embrace. So fundamentally, my view is that if you take EnerPHit as a challenging standard, it is a challenge to meet it. But actually by setting the bar really high, you're more likely to get a better outcome than simply just saying, well, we can't meet it, let's just do business as usual. Set the bar high, you'll achieve higher. And that's really, for me, the main reason that we've looked to go down the EnerPHit methodology. The project itself isn't Passivhaus certified, just got to get that point across. We've taken it to the contract stage with the third-party verification of a certifier, and from that point on, because we couldn't meet the criteria for various VE elements, we've not had that process through the site. But what we still feel that we've achieved a much better outcome than we would have if we had done business as usual. And it's also gone on to future projects. So just down the road from Woodside is a 1920s retrofit where we've applied a lot of the principles we've learnt there. Again, not a certified project, but we're using the EnerPHit stepwise approach here. And then by doing so, we've actually got to a point where we're able to produce more energy than we consume annually. And it's led also into the formation of collective energy last year, so that we can collaborate and share our sustainability goals with others. Thank you.
That was fantastic. I loved the fact that you told us not only the general principles, but we actually saw exactly how you tackled each problem on those buildings. I just wanted to ask you a couple of slightly general things before we go on to the conversation with the others. I mean, you talked about the form factor on the Woodside flats, and you said that was of great benefit when upgrading them. Obviously helped you get towards the EnerPHit standards. And also you said they were surprisingly airtight, although not airtight enough. Do you think we're underestimating the value of this type of building? Because they are the sort of buildings that a lot of people look at and are not very cheerful about. And, you know, there have been rather a lot of cases where people have been blowing them up and replacing them.
Yeah, I think each one's different in a way, because I think where these are located, they're fairly central to Glasgow, walking distance, lots of transport on the doorstep, and great amenities. And what we undertook at the start of the project was quite a vast community consultation. And we realised that a lot of the stigma associated with these high-rise buildings was actually external. It's not people living in the buildings, it's people who are from outside. And in Glasgow, we've had a bit of a history of, as you say, blowing up certain high-rise buildings. But we felt from doing the community consultations, the occupants were generally quite happy with living in such a central location to the city. There was obviously issues with mold, damp, cold, drafty and unaffordable heating, which we were looking to tackle. But the main element that we had to look at initially was making sure structurally that they were sound. You know, we have to be careful that we don't spend a lot of money retrofitting a building which is only going to last a few years, because there's integral problems. You know, so this one, we know that the structure is going to be fine for another 50 years. You know, so we're good to go.
That's really interesting. And I think you've also reminded us that social sustainability is very important too. There's no point in retrofitting buildings if nobody wants to live in them. I think of all our speakers, you're probably the most enthusiastic about EnerPHit. And I just wondered, you talk about other projects where perhaps they won't go the whole way because they can't afford it. Does it bother you that EnerPHit is a bit like the Rolls-Royce of retrofit, and that too many clients are deciding that they can't afford it, when you're really seeing it as very much the way to go?
I think there's a little bit of a misnomer in that it's either all or nothing. So a lot of people are like, can we meet the certification criteria? And if people say, oh, it's going to be almost impossible, then people say, all right, let's forget it. Let's scrap it. Let's go back to business as usual. That's the bit that gets me. I think there's so much value in the methodology. And if everyone's chasing that sort of challenging number and deciding that they can't make it and just giving up, then that's the worry. The good thing with the methodology is, even if you don't get to that number, you're getting to a much better sort of energy efficiency and a much better comfort for the occupants than you would be otherwise. So I initially was hung up on trying to achieve the certification because it's a great thing to have, but it's not actually the important factor. The important thing is the quality assurance and being able to have those discussions and know where to spend the money most efficiently. So we're not wasting time and money, and we're not creating a future retrofit waiting to happen by doing an undeveloped sort of minimum compliance approach.
Thank you very much. I think that's probably the point at which we should bring our other speakers back in. I think there's more to discuss on that point and on other points. So there we are. We're all back. I'm going to circle back to Lee's presentation first, and I'm going to put something to him, which I think probably the other two of you will be able to add as well. And I'm going back to this point you made about well, you can be a bit pragmatic, and if you don't want to do quite as much insulation because you feel it's too expensive, then actually it may work to put some more PV on the building instead. You gave us a lot of figures, but we did get a challenge come in actually on Twitter from someone who said, is this really what a sustainability, a consultant who claims to be interested in green buildings should say? Now, I think you've got quite strong reasons for that. I think it is pragmatic, but I think they're probably quite practical reasons. And since you've been challenged, I'm going to push that challenge to you and say, how can you justify saying this?
Okay, it's a great challenge, and one we deal with on a daily basis here, or practice. And if we consider sustainability and insulation in that regard, with any technology, and insulation for us is just another technology to apply to buildings. With any technology, there's a tipping point where it becomes unsustainable to install it. It's not adding significant enough environmental gain to justify the extra cost of that technology. And so what I would always say is, when we're looking at these technologies, is try to understand where the sustainable tipping point is, where it becomes an excessive technology at the detriment to the environment rather than a sustainable benefit to it. And that would be my answer to that question.
Thank you very much. Do either of the others of you want to add anything there?
Unlike with the air source heat pumps or heat pumps,
which we will go back to in a minute.
Sure, yes. So adding a solar, and probably even more importantly, solar thermal, does no harm, or rather does not contradict the building's ability to retain heat or not lose it. So if you can, a very pragmatic approach, if you can get some free sun warming your bath water, why wouldn't you? you know, and it goes, and in fact, you at the moment get renewable heat incentives for that. So this changes again, like government policies do all the time. So at one point it was PVs that got renewable heat incentive. Now it's only solar thermals. But so that's what I would say. If you can, why wouldn't you?
I'm going to actually surprisingly possibly agree with Lee a little bit on a tipping point. But what I mean on that is there is a point at which it isn't it just gets too expensive to just keep adding insulation, and that's what the EnerPHit or the passive house reason we're not aiming for zero. You know, we're aiming for a low level, but it's what's considered sort of reasonably effective, and we can achieve it. But if you take Woodside, for example, and the U values that you were using in your presentation, we actually have a wall U value of about 0.25, which isn't down at the 0.15 that we're saying. And that's the pragmatism of the whole system approach of looking at passive house. We're not looking at an individual component, we're looking at all of the components, and we're achieving an energy balance across that. I think renewables are great. I would prefer to see them used for things like the things that we can't reduce significantly, like the electricity usage or the hot water usage, as Sanya had mentioned there. And when you think about it on a building level, we've only got so much space to put in this equipment. So if you're using it to offset the heat loss from the building, which you could actually do with putting in insulation for the lifetime of the building, then you're not using that space for the other energy uses in the building. And if you said, well, actually, we could just put it at a national level and use renewables through the grid, well, that's possible too. But if we don't get the actual demand down, the grid doesn't have the capacity to do that in all cases. There will be buildings which we can't get down, but we should be optimizing the buildings that we can.
Thank you very much. Now, I'm afraid we are going to go back to these air source heat pumps, partly because we've got 2 more questions about them, and partly because I'm still very confused, and I'm going to see if I can get to a point where I understand what is possible. I do understand how it works, for example, in the project that Sanya showed us, although she had hell with the planners. But these 2 questions that have come in, I think, really highlight some of the problems. One says, what alternative is there if wishing to change a gas boiler in an existing house heating system, which has a traditional piped low pressure hot water system, without changing the radiator heating system internally? And the other one says, Sanya mentioned that installation of an air source heat pump on its own without fabric upgrades will not provide significant improvements in energy use. However, are they not a worthwhile consideration where a gas boiler needs to be replaced anyway? And I would add to that, and again, I think this is often an issue with buildings which are not getting the sort of thorough overhauls that you guys are talking about, not being ripped to pieces, but just need a replacement. And the third thing I really don't understand is most people replace their gas boilers as a distress purchase, don't they? It's just packed up, and they need a replacement. And the idea of getting an air source heat pump in all of a sudden by next Wednesday, I do not understand at all. So I'm going to bat that back to Lee.
Okay, thank you. If I talk about existing buildings just now, quite a lot of our existing housing stock has very aged heating systems within them, sort of pipework, radiators, and they were probably, on the whole, that pipework and some of the radiators installed whilst the property had either very poor double glazing or single glazing. And once you upgrade your double glazing in your property, either to a more modern version or move away from single into double, quite quickly what you've done is you've reduced the heating demand within the building quite considerably, and maybe by as much as 40%. What that then means is that your radiators are already oversized for the home that you're living in. And the strong possibility is that the radiators and the pipework that is there is of sufficient capacity to run an air source heat pump at lower temperatures. On more modern builds, what we're finding is that plumbers, as it were, are still installing radiators that they would maybe 10, 15, 20 years ago into spaces. So again, they're already quite large for the space that they're going into. And with a proper survey and a proper piece of work commissioned on the home, you probably find that it's very, very low cost to install air source heat pumps in the property.
I'm going to go on to my next question, which is that we had somebody come in and say, is it possible to do an EnerPHit refurbishment to a building that was built before 1930? Now, I think 1930 is a really arbitrary date to have picked, but I guess the wider question, and I would be interested in this, is are there buildings that you really cannot refit to that standard without spending a ridiculous amount of money? And I suppose the other question I will put in is that one of the things we haven't talked about, and I think this came up in one of the questions, in fact, relating to PV, but it relates to the whole thing, is are we looking at the embodied carbon of these retrofits as well? Are there places where we're actually generating so much CO2 in retrofitting that it's just not worth it? But first of all, I'm going to say, are there buildings that really cannot be retrofitted to these standards? And I'm going to start with Sanya.
I think I would refer here back to Rupert. Thank you. Yes. Only because we stayed away from using it ourselves. But I totally agree with Rupert that it is not necessary to use the whole hog, but use it as a guidelines principle. Now, we do it as our own in-house EnerPHit kind of process developed over the last 10, 20 years. And it's not numerical in a sense that, and it doesn't produce beautiful diagrams, but we have a hierarchy in understanding which elements of the building are most efficient and contribute most to heat losses. And when you're saying pre-1930s, it probably means solid wall. And by all means, it is absolutely possible to improve significantly a solid wall construction with a thorough, holistic approach. Now, whether that's applicable to through EnerPHit or without whether that's applicable in EnerPHit, I don't know. Rupert.
What I was going to start with was the last project that I showed there is actually built in the 1920s as a solid wall. It was a former printing press. We've managed to wrap it in insulation. It's stepwise, so we're not actually at that level because we're only on step 2. We've still got other areas to go to, but in principle, yes, we could get that building down to the EnerPHit levels. There are a number of pilots going on around the country. Here in Glasgow, I know Nidri Road, which is with some contemporaries of John Gilbert Architects, is a full close tenement refurb to EnerPHit standard. So that's sort of the testing pilot bed to see what's required and the costs involved in doing so. So it's and I think we're at a point where we're essentially needing to build up a series of typology pilots across the country so that we can just evidence how it can be done so that it can be rolled out sort of at mass scale effectively.
And Lee, I think I'm going to put to you the part of the question about the embodied energy that is going into some of these retrofits, and whether at some point there's a concern that you're putting so much embodied energy in that your savings are on energy and operation are not really worth it.
I suppose I start by saying one of my favourite construction technologies is the very simple Cafferata brick that was used quite heavily in the intervening in between war era and sort of early part of the 19th century and thereafter to build many houses. That brick has lots and lots of energy embodied within it, but we're still using them and recycling them today. So I would always say, well, if we're going to use technology, we're going to use product in buildings, well, I'd rather we use product in building that would last 100 years, 150 years and could be recycled, can be part of the circular economy, as it were. And I think if it has a high embodied and it lasts for numbers of generations, then I think it's a worthy investment because we're locking that energy in and we're reusing that product over numbers of generations. So that's how I would answer that question.
Someone's asking, are the residents using the MVHR properly? And this question that says, from my 13 years experience in social housing, many residents disliked mechanical ventilation systems and turned them off, which led to severe condensation problems. Don't know how much of that you've gone back and looked at.
We've actually just started. I think we had a bit of a setback, obviously, with COVID and lockdown restrictions, but we're looking to go back in now. And that's in some ways that's why we've gone down this route, is we're trying to mitigate the problems with industry standard install. We did post occupancies on previous projects and realized that noise is a big issue with MVHR or any mechanical system for that matter, and social housing. Tenants tend, if they hear it, they think it's costing them money, and so they might switch it off. So we've gone to quite a lot of effort to ensure that it runs, it's not switched off. And I think we're going to be going back in to do some post occupancy and review how effective it's been. But the general viewpoint from some of the residents that we've spoken to is they're understanding the benefit that it's providing to them in terms of air quality. I mean, in some ways, it's an easy sell when before we did the work, they had black mold on window sills. So if we're saying keep the ventilation on and you won't get that, that works quite well. But I think there is a bit of a learning curve for the industry to make sure that we're getting MVHR installed effectively, and the issues with the likes of noise are dealt with. The efficiency, I just want to pick up on one of Lee's points there. I don't quite agree with the being maximum 30% efficiency, but I do agree with there being net efficiency of the unit and then gross efficiency of the system. And I think that's the failing on the industry at the moment, is we're always quoting the SAP's net efficiency, but we're not fully designing the gross efficiency of the whole system. And that's again where there's more benefit of using the Passivhaus methodology, because you can have inputs for the rest of the system.
I'm just going to sneak one more question in quickly to Sanya that's just come in. Again, it's about going back and measuring, and questions just wondering, is there any energy and use data to show how your retrofit work has improved the building, either relative to before the works or even relative to EnerPHit? Now, I think maybe EnerPHit, which you don't really use, is not the question, but the questioner is saying it's important to understand relative to your qualitative method. And I wonder if you've got any figures and you have gone back to your projects.
Yes, we definitely have the figures of the project from 2010 or 2012. And it's very easy to compare first the number of occupants in the building with, and then secondly, the bills. We now have, pre the retrofit, we had maximum 4 occupants because it was a one family dwelling. It's now house and multiple occupancy plus an office. So we have at least 10 occupants, and it's occupied, pretty much 24 hours a day. The bills pre-retrofit were, and we did that, admittedly, about 8 years ago when we applied for one of the awards. I can't remember now which one. The bills were 3 times as much in the pre-retrofit time, despite the occupancy being lower and the hours of occupancy lower than they were after the retrofit. And with the other property with electricity spent only, again, we can't compare to pre-days because it was unoccupied for 2 years. But if I just say it's 3-bedroom property with 3 to 4 inhabitants, and it spends about between 50 and 70 pounds per month on electricity bills. There are no other bills. So I would say that's pretty good. It's about 120 square meters, and I'd say that's just comparing to other properties and their bills, I'd say that's a pretty good going.
Thank you very much. And I think that's a lovely positive note on which we can end. We've heard from 3 experts here who really are tackling these issues, and whether they've asked or answered the question, is EnerPHit the answer? But I think they've also shown us the ways that you can tackle these things with knowledge, with hard figures, with the use of sustainability consultants, and with fantastic attention to detail. I think that's been a very positive event. I'd like to thank all 3 of our speakers. I'd like to thank all of you who are watching this, particularly the people who sent in questions, but all of you just for giving your time to listen to such an important and interesting discussion. And on behalf of Architecture Today and of Schu, I'd like to thank everybody very much and look forward to seeing you again at future events. Thank you. Bye.